Algebra 2, Unit 1, Lesson 5. We're skipping Lesson 4. It does technology and some stuff like that, but we just want to get right to the good stuff. So we're going to go right to Lesson 5. Lesson 5 tells us that we're going to start to turn sequences that we found into functions. Okay, so this is that connection to yesterday that we started seeing, where they reminded us about function notation in the warm-up. Remember this yesterday. So in lesson 3. So we're going to start looking at some function notation. We're going to use f of n and things like that to talk about the function that defines a sequence, and the n is going to be the term or the input that we're using. So we're going to have a term. It's going to have some kind of a rule or equation that's going to help us describe to other people how you make one sequence, how you find one term, just like that. So if we are bowling for triangles in part 1, describe how to produce one step of the pattern using the previous step. So if I compare these two, I can tell that what they did is they added 2. And then from that step, they added 3. And then over here, it looks like they added 4. Okay. So I also notice that the number that they're adding is the same as the step number. So I think that that's interesting. So if I were to describe how to produce one step of the pattern based on the previous step, I would add the same number as the step number. Oops, that's funny. I would add the same value as the step number to the previous step. So my sequence would look like, if I'm turning this sequence of dots into steps, I've got step and I've got number of dots. Step 1 has 1 dot. Step 2 has 3 dots. Step 3 has 6 dots. Step 4 has 10 dots. And I just fell off the page. So here's where I'm going like +2, because that's step 2. Step 3, we added 3 to the prior one. Step 4, we added 4 to get that. So for step 5, we would add 5 to get this number. And we could keep going. Now this is one way that we can write functions, is to know what the number is that's previous to it, the previous step or the previous term, and we can tell it what to do based on the previous term. Okay, that is what we call a recursive definition. Okay, so you see that vocab word right here. A recursive definition of a sequence. That's how we're going to define a sequence, how we're going to describe it. Recursive means that we have to know the prior term before it. So I have to know step 1 in order to calculate step 2. I have to know step 2 to calculate step 3. I have to know step 3 to calculate step 4. Now there's times where that's going to be okay, right? Where we can just make a pattern like this, and maybe we only want to find step 5 or step 6, and we can do that math. But there's going to be other times that we'll be like, well, what happens in step 100? That's a lot of math. Okay, so later we're going to find a different kind of term that we don't have to know the term before it in order to calculate it. But for today, this is where we're starting with. So here's our visual pattern of dots. We just said how we were going to do it. And it's all about step numbers. So when it asks us what values make sense for n in this situations, well, if n is our step number n, and we're going to be writing a function d of n, like dots, as a function of the step number, which is exactly what I used right here, step number and dots. Our value for n would only be whole numbers. Decimals don't make sense here. I can't add like a half a step between 3 and 4. I don't know what that would look like. That's weird. So whole numbers greater than 1. I don't want to go to negative whole numbers. I don't know what a negative step looks like. I guess I could go backwards, but going backwards from here, I don't know what that would look like. I mean, I could go to 0, but then I can't go negative. So negative numbers don't make sense. So whole numbers greater than 1 are what makes sense here. So if we were to complete the table from steps 1 to 5, they're already giving us some information that we're going to take the previous term. That's what d of 1 means. It means we've done d of 1. This is step 1. D of 1 equals 1. And now we're taking that number and putting it here and being like, okay, well, 1 plus 2 equals 3. And now to find the next one, this is telling me that d of 2 is 3. When I put 2 in the second step, there are 3 dots to it. So d of 2, that's what this is saying here, d of 2 is 3. And if we add 3 to it, we get 6. If I just keep filling out the table with that same pattern, this is saying if I take the prior term, d3, and this time I add 4, I'm going to get 10. Because we already said step 4 has 10 dots in it. And if I take d4 and I add 5 to it, I'm going to get 15. Take that prior term, add 5 to it, and get 15. So following the pattern in the table, write an equation for dn in terms of the previous step. And then we have to explain our reasoning. Okay, so to find d4, we had to know d3. So to find any step n, we have to know the step before it. To find step d of n, we have to take the step before it, dn minus 1. So to find d4, I needed d3, that's 4 minus 1. And then I'm going to add whatever the step number is to it. Okay, because that's what we said on the other side here, that we're going to add the same value as the step number to the previous number of dots. We're going to take the previous number of dots, we're going to add whatever that step number is, and that's going to get us our new number of dots. So whatever is our new term, we take the prior term, the previous term, and we add a certain number of dots. There's another part, though, to a recursive formula. Since we're trying to write this equation, we have to give it a starting point. Because if everything is based on the term before it, if I'm like, hey, here's a rule, what's the next number? I'm going to be like, well, what's the first number? I don't even know where to start. So if we have a recursive formula, we're going to have to always tell us where to start. So the first term is 1. Notice how I set that like this, that the first term of this sequence is a starting value. I'm going to give you a number. And so since I need these two things to work together, we put a fancy bracket in front of it to say, hey, these things have to go together. So you know where to start, and then you've got instructions of what to do with it to find the next term. Okay. So it's telling us that we're now going to have our n is our input. Our d of n is our dots. I just want to double check it and see if it matches up to the numbers that we were getting before, just to make sure. So d of 1, I know equals 1. When n is 2, so I'm going to start that here, is taking d of 2 minus 1 in parentheses, and it's adding n to it. Well, n is 2. Okay, now d of 2 minus 1 means d of 1 plus 2, and d of 1, we already said equals 1, so it's 1 plus 2. So it's really taking a lot of different steps here and kind of combining it together. So for my third step, that's telling me I'm going to just replace all of the n's with the number 3 because that's what step I'm looking for. D of 3 minus 1, which is d of 2, which we already said d of 2 is 3 dots. But I also have to add n. I have to add 3 to it. And I am getting that same pattern going on here. All right, we're going to keep on practicing this, no worries. If we're going to define some sequences in 5.3, use the first 5 terms of each sequence to state if the sequence is arithmetic, geometric, or neither. Then define the sequence recursively using function notation. Okay, so we're going to be using some addition or some multiplication if it's arithmetic or geometric. So start off with what we know. Take a look at the pattern first. Find the pattern. Each one of these things, we've seen this pattern before, we're going to add 10 each time. So this is an arithmetic equation. To define it recursively, I'm going to use A because that's what they call this sequence. I'm going to tell you you're going to start off with the number 30. I always have to tell you the starting number with a recursive sequence. For every other number past that, you are going to take the prior number, the prior term, and you're going to add 10 to it. So start with 30. For my next term, I take 30 and I add 10. For my next term, I take 40 and I add 10. For my next term, I take 50 and I add 10. So that's what this is saying. Take the prior term, add 10 to it. Sequence 2, or sequence B, is multiplying by 1/2. Remember, you can take any number and divide it by the one before it to find out what it is. We could also say it's multiplying by 0.5. We could also say it's dividing by 2. I'm going to stick with this stuff. This is geometric. And with a geometric function, we can still use recursive. We still need to know what it starts with. This is sequence B. So it starts with the number 80. And now to find every term after that, we're going to take the prior term, B of n minus 1, and we're going to multiply it by 1/2. Now there's lots of ways to write this. We could do 1/2 of bn minus 1. Or we could do b of n minus 1, the prior term, all divided by 2. All right, our next one, multiplying by 2, it looks like geometric function sequence C starts with number 1, and to find every term after that, we're going to take the term before it, and we're going to multiply it by 2. Again, we could put it in front. We could put brackets around C of n minus 1. Lots of ways we could represent it. 1 becomes half, becomes a quarter, becomes an eighth, becomes a 16th. Let's see. The numerators stay the same. The denominators double. So we're multiplying by half again, cutting everything in half and half and half and half. So if this one stayed with even numbers, we would go there. All right. Multiplying by half. That's looking an awful lot like this one, but notice that we're starting with a different number. So we have a different sequence definition. Oh, this is geometric. D of 1 is what we're starting with. Then to find every term after that, we're going to take the term before it, and we're going to multiply by 1/2. Notice all of our geometric ones use multiplication. Our arithmetic one uses addition. Good way to also tell that difference. All right, what's going on here? Sequence E. Looks like it's subtracting 7 each time. This is arithmetic. It adds a negative 7. Sequence E starts with the number 20. And then every term after that takes the 1 before it, and it subtracts 7. Do you see how important that warm-up from yesterday is starting to look like, the warm-up from lesson 3? When they were telling us the difference of like putting it in parentheses so that's the 1 before it. So here's that number before 10 and it's 9. But here's the whole previous term and then subtracting 1. So what those look like, they're pretty smart here when they designed this curriculum. So that's what that would look like. All right, one last one. Let's see, times 3 times 3. Okay, not doing that. Looks like it's adding 2, adding 4, adding 8, adding 16. Okay, so each time it's doubling how much it's adding. Ugh. This is neither, because it's using addition and multiplication. This looks like a mess. But I can tell you that it starts with the number 1, and it looks like it takes each next term, takes the term before it, and it adds well, let's see, this is 2 times 1, this is 2 times 2, this is 2 times 4. Ugh, that's not good. This is 2 to the first power. This is 2 squared. Oh, all right, this is 2 to the third. Gosh, I don't know that I would ever get that. Let me double even check that because I'm not convinced of myself And this is how we check stuff as we go to the calculator. Ugh. Sorry, I was doing all kinds of stuff. 2 to the 4th power. Oh, it is 16. Okay, good. So I got that right. So here's the first term is 2 to the 1st is what it adds to get to the second term. From the second term, we add 2 to that second power to get to the third term. So we're adding 2 to the nth power minus 1. Ugh. That one's really complex. But we can see that to get to 1, 2, 3, 4, to get to the 4th power, we had to add 2 to the 4th power to get to the 5th. So to find each term, we need to multiply it by 2 to the... My brain's hurting. All right. There's our summary. So they start talking about how we can find the nth minus 1 and how we can add addition. They can tell that this is an arithmetic sequence. If we've got multiplication, we're going to do some other stuff going on here. So they're going to tack this n greater than or equal to 2 at the end because you can't kick in that use your prior term until you have the first term. So I forgot that, I guess technically. For each one of these rules, I should say for n greater than or equal to the second term. Because I have to give you the first term, and then for the second term and everything after that, we can use a rule that tells us what to do to the term before it. All right. Go try some practice problems. It's going to go great. I believe in you.